Hello to viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about refractory cement. So let's dive deep into it. Now, what exactly is the problem that we are looking into refractory cement rather than just porcelain cement? Yeah, we need to deal with high temperature, and I mean high temperature as in really high, as in metal melting temperature. So, and here's the deal. It's not like once in a blue moon. No, it's a regular. It's like every day, 24 into 7 into 365 kind of deal. So this is something that is needed in many fields and many tasks. It's not optional. It's not like luxury. It is like necessity. And what do we mean when we classify as refractory cement? Generally, it simply means the high temperature environment should be natural to it, meaning it should not be under stress. Because again, technically concrete can handle some high temperature, even I'm talking basic one, but it cannot handle it for long. Because again, the way it is, it's like, yeah, like if you have a big boom event, it's like, big fireball, it's like, I got this. But if you are like furnace kind of scenario, it's like, yeah, I did not get this. So that's the whole scenario. It has to be natural. It has to take high temperature. Like, it does not matter. There should not be any thermal degradation, as in you must have seen there are a lot of people who have tried to make soldering irons. Station, we got this, no problem. Soldering iron, nobody has succeeded because most of them use fiber sleeve. They have the main conductor, they put a fiber sleeve, and then they nichrome wire. Cool, awesome. Here's the problem. To dump energy, like let's say you want to achieve 400 degrees Celsius into the tip, you have to have nichrome wire much higher than that. And because you have an insulation layer, it increases the temperature even more. That generally crosses 500 degrees Celsius, and that sleeve is not designed to handle above 500 degrees C for long duration. It will char and it will fall apart. We use mica generally. In older soldering iron, we use mica sheets. They're expensive AF, so most people don't try it. So that's why you will rarely see somebody making a quality soldering iron. Station, got this. Iron, no. So we need something that is what we call thermal degradation proof, as in like for the working temperature. It should not be like, oh, it can only work for like 5 minutes. No. For here, like it should be a normal stuff. Like it is here, it keeps working. If it cracks, we repair it. It's like it's a thing, normal thing. And it is the core of our ability to do things in a natural world. Basically, if you want to make wood, you grow a tree. Wood is natural element, but again, it has limitation. Now, if you want to deal with metal, ceramics, bricks, all these things exceed natural ability. At that point in time, you need high temperature. And I'm talking starting at 500 or 600 and going to even higher than that. Like ludicrous temperature, 3000 degrees Celsius is required sometimes. So it has to be stable, no thermal. And be mindful, humanity has figured out surprisingly early that we need this. And I would say, give or take 5,000 years ago, we have been building kilns, things where we cook pots, clay pots and all that. And like, do we need to cook them? Yes, that's the first thing we realize. You can make a clay pot and dry it, but if you cook it, like very high temperature cooking it, it becomes almost like a crystal, almost like a cement, porcelain kind of thing. And it's like very stable, very long lasting. Like we learned it the hard way. And again, same happened with bricks. Wood houses, cool and all, but like bricks is like, bro, I got this. Glasses, metals, we learned this the hard way. Like if you cannot make a furnace, you cannot do it. And again, why do you need a furnace? Simply because if you do not have the insulator, no matter how much fuel you burn, you will leach out energy too quickly into the ambient. You will not be able to reach high enough temperature. Meaning if I give you 10 kilowatt power and I give you 100 unit of electricity, you should be able to reach any temperature you want as long as you can insulate it. And you're like, wait a minute, we spend more than that to heat our homes. Yeah, it's not perfect insulator. That's why. And again, you want it to be not a perfect insulator because you do not want to boil in your home. So that's the problem. So what are our friends here? Our friends are oxides. To achieve molten state of any material, you have to exceed the material's melting point. Meaning if you are dealing with, I want to make steel, average stuff, 1600 degrees Celsius. That means your kiln must be above 1600. It will not be like, okay, kiln is at 1600. It might plasticize steel, but it will not melt it. So if you want like melting, you have to exceed it. It's a common thing you have to pay attention to. Same happens with soldering irons. Like the solder is like, okay, 200 degree, it will melt. And some are like even lower than that, 180, it will melt. Why the heck soldering iron tips has to go to 400? It has to, so it can dump energy quickly enough. The T delta, higher the T delta, the quicker the energy just whoosh, floods it. That's why if you have a high power soldering iron, it's much quicker. If you have slow one, it destroys the board. So same things. Now oxides are best choice because they are already married. They are already at low energy state. Like you have a material, it has already oxidized. There's not much is gonna do. Like it's stable. It's a electron orbits. It's a compound stability. It's like, bro, we done. It's like we done. So it's very stable and inert at high temperature. This is one other aspect. Most things are stable in normal day-to-day temperature. However, even those most things, if you start to heat them up to very high temperature, let's say 1000 degrees Celsius or 1500 degrees Celsius, they start to behave and they have reactions that like will confuse you. Like you could have a glass that can eat away things. You can have a slag that can just react to the materials. So it creates a very serious scenario where it's like, yeah, we want an insulator that can handle this temperature while being inert. So oxides are the only reasonable choice. There are some ceramics like zirconium, but they are idiotically expensive. Not expensive, idiotically expensive. So you have silicon dioxide, one very good choice. Second, alumina oxide, really decent choice. Magnesium oxide, low cost choice, but really effective, cost effective wise. And then we generally have some sort of binder. Now binder could be temporary, just to give it form until you cook it, or it could be a permanent part of it. So these are the oxides that we use. And yes, all of them look like white powder. That's what we are talking about. So keep that in mind. Even if you're like, hey, I need like 3000 degrees Celsius for, let's say, melting tungsten, you might require more than that, like easily more than that, like 3500 degrees Celsius to actually melt it, something. So that's the core aspect that you must pay attention to. Oxides are your friend here. Okay, then how the heck we make from oxide to useful stuff? Barrier between hot and ambient environment. That's what you are working on. You generally do not want to use your fire brick as main structural element. You want to have normal metal or normal bricks to do the structural part, and you want this to be an insulator layer. It's like fire, I keep you at bay. So, and again, there are fire bricks that are designed to be more of a load bearing, but they have lower insulation grade. So it's up to you. Depending on your choice, depending on your requirement, you could choose one or the other. And must have to be compatible with use case. This is where it becomes a art form, because if you go into any manufacturer that is decently good, it will have like, yeah, we have 15-16 options. It's like, what the hell? That's the reason behind it. Because especially if you're dealing with anything touching it, let that be clear. If you are like, hey, I have a crucible and things are happening inside the crucible, and crucible is the consumable part, you do not need to worry about too much about the environment unless you are using fire. If you're using fire, depending what fuel you are using, does that fuel have some naughty things? For example, let's say you was using bunker oil. Yeah, that puppy has sulfur like there is no tomorrow. So you have to handle it. So you have to deal with acidic slag or basic slag. And if you're dumping stuff like metal is actually touching it, ooh, it's a completely different ballgame that you have to deal with. And it must withstand the chemical environment. Because of the high enrichment, basically the high stuff that is happening, everything becomes dangerous at that temperature. Like even salt. Even normal salt can become destructive at that sort of temperature. And people generally do not cheap out on it, simply because if they're smart, they know that higher the insulation, cheaper it is to run. Even if the capital cost goes up, the running cost goes down. A furnace consumes energy. It could be chemical energy, it could be electrical energy, but it will consume energy. So the more energy you radiate out, the less energy stays in. The more fuel and more energy you have to consume in order to achieve the temperature. So if let's say you have a furnace and outside of furnace is not close to ambient, let's say ambient supposed to be 50 degrees Celsius, but the furnace walls are like 150, yeah, you did something wrong. Furnace wall, again, it will be warm. You cannot design a structure that is like, no. You have to have vacuum insulation and reflectors, so to make sure that radiation can be bounced back and there is no gas molecules bouncing around. But you should be able to drop it to 70 degrees Celsius. Basically human safe. As long as person can touch it without kaputting itself, it should be fine. So that's the whole point. If you're leaching that energy away into the ambient, you have to spend more energy putting it. So higher the insulation, cheaper it has to be. How do we achieve it? Well, alumina, generally in this sort of scenario, we take it into a powder form, we put some binder into it so we can give structure, and we design this, what we call closed cell. It's not hollow. It's not like gases cannot go through from one side to another. So you have open cell foam, you have closed cell foam. Think in that way. It is closed cell foam. So there are a lot of small gas pockets, so to say. And energy cannot jump from one to the other. And you're like, why not use oxide itself? If you use condensed oxide, like it's a brick of oxide, pure oxide, yeah, it's a conductor actually at that point in time. Not a great conductor. It's not nowhere near as aluminum. It's like it will still be 1/10 of it. but it's a conductor, not an insulator. So you have to have gas pockets. That's why these bricks are very lightweight, even though they are made out of heavy stuff, aluminum or silicon. Those are not lightweight stuff, especially aluminum. Magnesium, those things are not heavy, but it has a lot of gas pockets. So those sealed pockets are acting as a barrier. It's basically the same strategy in re-entry heat tiles. They have carbon as like that handles the radiation and all that, and then you have gas pockets. Gas pocket is the one that is stopping thermal flux from traveling from the outside of the tile surface to inside the metal case. So same thing is happening here. You need that gas trapped, otherwise like gases will just leak out. So fire bricks, that's how we create it. We take your oxide material, you put it into a binder, you create a shape, you create enough pockets, and then you cook it. Cooking simply sinters the particle, one particle to another particle, and it retains its hollow structure. Again, I have not found any electron microscope image of that. Sorry about that. So it looks like this. So this is the fire brick side of it. And be mindful, you have to select based on your requirements. So pizza fire brick would not be suitable for basically, if you're melting reactive stuff inside. Now here's the deal. That's one use case of ceramic insulators and refractory materials. Another is insulator. Now sometimes we have a contradictory requirement. For example, generally things that are good at dielectric, they're also good at basically being a thermal insulator. But what if you need opposites? As in, I want this puppy to stop electricity like there is no tomorrow. Like electricity shall not pass. You shall not pass. But heat, go away. So you need something that can conduct heat very effectively, but block electricity at very high electrical load, high dielectric strength. So ironically, refractories are surprisingly good at that. So this times when you need thermal conductor, temperature conductor, and which is very dielectric, alumina is your friend right now. And where do we use this sort of odd combination? Heating elements. That's why I said nobody can make heating element in home simply because these heating elements have nichrome wire. Cool. But here's the deal. If you have nichrome wire directly wrapped around a pipe in a desoldering iron or at the rod, it will short. So you have to have an insulator. Old days we used to use mica. Problem is mica is not a solid mass. So it has a lot of micro voids. Penalty of that is your nichrome wire overheats in order to dump enough heat. So this solves that. It's a solid mass. Now how do you achieve this solid mass? Generally you can compress it, whereas you have the powder, very dry powder, and you what we call press forming it. You have a structure, you just it. So that way you get a complete solid mass. Particles are sintered together in compression, so to say, and the heat is isolated electrically. So you can even have AC mains power, 220 volt. You don't have to go to low voltage. 220 volt power, GG, awesome heat. And again, it consumes less energy. Why? Because nichrome is able to dump its heat into the outside body very quickly. And again, if you look into cartridge style system, that's why they always have nichrome wire and white powder. That white powder is this. That's why they can work so effectively even as low power as 20 watts. So you have to be mindful. You want your heating element to dump heat quickly. So that means it must have something that is electrically insulating while thermally being conductive. So back in the days, for example, PCB boards, they were made out of what we call fiberglass 4. Now, those are good. They work. Most of your stuff is made out of it. But here's what if you want to make a LED panel? Yeah, it's not great for that. Why? Well, it's not an insulator. It's not a conductor of heat. It's an insulator. We want insulator. Here, if we use alumina, it is 20 to 30 watts of thermal conductivity. So if you have LED diodes, it leaches heat very quickly and it is electrically stable. As in, you can have 220 volt on top of it. It's like, bro, I got this. Actually, you can have kilovolt. These things are used in high power lasers and microwave stuff. It's high power, high voltage. It's bro, don't bother me. It's flat out don't bother me. So that's why we use refractory materials, ceramics, specifically alumina for this sort of function. So you have nichrome resistive wire inside a ceramic stuff. Tada! It actually overheats the nichrome wire, but it saves in another way. For example, it will heat the wire to be much higher temperature. If it was air blowing through it, this will be higher temperature, but it is completely isolated from any changes. It's not expanding or contracting because it's encapsulated. It's not reacting to oxygen. It's encapsulated. There is no moisture landing on it or boiling away, nothing. So these sort of elements, what we call ceramic elements, can last very long. Does come with a penalty that they do not go as high temperature because again, the element may already has reached melting point. So temperature wise, they are not that good. Longevity wise, they are awesome. Meaning if you need a furnace that only goes to, let's say 500 or 600 degrees Celsius, these are awesome. You don't have to, you put it, forget about it. So heating, and again, power IC cooling, lot of things. Basically, substrate material is being changed with refractory material. So all the MOSFET, all the system, you do not have to worry about, hey, it's causing short. It's like, bro, I got this, be good. And it can leach heat away very quickly. Now, again, it's not as quick as aluminum, but it is dielectric. So it can actually be utilized. If you directly bolt all the material into aluminum heat sinks, it will short out. So fundamentally, you either do void free casting. Now sometimes, especially for this sort of element, they use a cement. This is what we call press forming. This is cement. I do not know what they are using. They're using alumina. That's a known quantity. I just do not know what is the binder here. So they are using it. And high thermal conductivity is key. It's completely different from fire brick. Fire brick is designed to be stop as much energy from traveling as possible. Here, travel thermal energy as quickly as possible, but block electrical energy. That's the requirement, meaning these sort of elements will be dangerous if it was like, again, we had mica based systems, and that's why those old soldering irons used to be huge. They had to be. They wanted so much insulation. These things are pencil tip, actually very slim. So this is the insulator. That's why, like, if you look into a lot of modern high power LEDs, they have, alumina substrate. It's leaching heat away, dumping into a basically vapor chamber or copper or aluminum heatsink is very quickly, because again, that initial slowdown of fiber board is now removed. It's far more effective. And again, these sort of heating elements, they last forever. Now here's the, these things may seem like, something that is like, only industry deals with. Here's the, there are a lot of formulations, meaning if you want to just start Googling fire brick formulations, you'll find few thousand of them. And I mean patented ones, not just like, oh, somebody is making it now, patented one. Like this is what company fought for kind of one. So you can make your own, lot of options. And mastery over refractory materials is necessary. Meaning, if your country does not know how to A, make raw alumina, B, does not know how to convert that raw alumina into a plate or heating elements, yeah, you will have hard time competing in modern world, like genuinely hard time, especially God help you if you want to work with what we call ultra high voltage DC, HVDC. Yeah, good luck. Without having this sort of mastery, good luck. And if you can't even make other things if you do not have good furnace and all that. So it is very necessary. Like if you live in a country like India, and unfortunately we do not have this sort of kiln in every colleges and all that, so people can experiment with it. It limits your like whole realm is limited to you, because everything that humans do, most of them requires above ambient temperature, like most of them. So we need to master it. Without this mastery, you don't have anything. Like just improving the insulation of a furnace by a few % would translate into magnificent energy savings, which could translate to either less fuel burnt, so less CO2, less electrical energy consumed, which means less fuel burnt. So fundamentally, we have to master it. And thankfully, magnesium oxide is a puppy that can make a cement directly, as in you do not need too many other stuff. And you need two stuff. You need magnesium oxide powder. I have ordered it. It has not arrived. It will arrive on 1 January. And then you need Epsom salt, which is magnesium sulfate. It did arrive. So these two things plus water, ideally buy distilled water, and tada, you can make a refractory material of your own. Meaning, why I'm trying this? Well, I want to be the first person to crack soldering iron. AC means soldering heating element. None of that like, oh, I have a rod and then I have freaking fiber wrapped into it. No, proper soldering iron. That's what I want to do, try to do. So it's a very easy stuff. Unfortunately, magnesium oxide is kind of a bit expensive. Now let that be. It is super easy available and it's safe. Magnesium sulfate, as in Epsom salt, used for muscle relief, relative aches and pains, and bath spa. So it is human safe. And magnesium oxide, ask your gym bro, they generally eat it. It's a supplement. That's the easiest way to find it. So it's safe, it's human safe. And you're like, wait a minute, if magnesium sulfate, magnesium oxide, both are relatively available, and all we require is water, then why don't we use it as a cement? Like imagine a house that just does not burn. Yeah, it is awesome. In temperature wise, this puppy is like, bro, below 1000 degrees Celsius, don't bother me. Like just don't. I ain't got time for this. And actually above that, just that I know the testing is till 1000, they don't even try it. Like, bro, it will survive that. It's very good. It even adheres to aluminum, copper, steel, like it adheres to it. Like it's a good stuff. It is just vulnerable to water. That's why we don't use it. Like if you have made out a structure out of it, over time water will dissolve salts from it, and tada, it will basically control Z into it. So as long as you're not dunking your elements into water, like I want soldering iron, and you're not supposed to dunk your soldering iron into anything. So it should work. That's the only penalty. Basically, if you have a furnace and all that, as long as you're not throwing water on top of it, it should be fine. And be mindful, it's not that it will directly dissolve if you touch water with it. It's just that long exposure to water is not recommended. Meaning, don't try to build in Vietnam rainy season or India sawan season. So there are a lot of reason to experiment. There's a lot of growth to be had. And like half of the time, if you read research paper, it's like, yep, 500 degrees Celsius, 700 degrees Celsius. How the heck you achieve that? Ta-da! And if you directly try to buy kilns, they're expensive. Even though heating element is not expensive, even though fire break itself is not expensive, is that whole procedure is so what you call rare, it's expensive. Like basically, the demand is very low, which creates supply that is even lower, penalty is very high prices. So that's why, like, I really like the fact that there are a lot of YouTubers who have actually made electrical kilns and that can reach decent temperature. One guy tried almost touching 1700 degrees Celsius. At that point, you can even melt so I am saying titanium. You can melt titanium. So there's a lot of experiment, and let's see. Wish me luck with this Epsom salt and magnesium. Again, I did not come up with the idea. It's Soros cement. I have linked the source video down below, but it's cool stuff. And again, people are trying to add some stuff that can make it water resistant. At that point in time, this would be good. Like imagine you having a building that's like fire, and it's like building is like bruh. Don't. And again, I mean, it can handle fire for long temperature. It's not like, 9/11 kind of scenario. It's like fire, steel is like, I got this. It's just that, yeah, at 700 degrees Celsius for long enough duration, that fire, they had fire insulation. Over time, it started to soften it and you had loading of the building. So that's why this will allow it to not reach that softening temperature. It's like, the steel structure inside will not reach the softening level. It will not be exposed to the heat. So let's just hope somebody can figure out how to have this without phosphate, that it does not dissolve in water. But it's a really awesome, good thing to do. So this was my presentation on basically refractory cement. Why does humanity need it? Mastery over it compulsory. I hope you have liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show my extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.